Previously, we were doing Maxwell's Boltzmann or your classical statistics, where the distribution was given by this. What was your G? G was basically what? Degeneracy. What you can think of this G as? G is just that small cell. Have we done previously? I believe we have done. Number of cells, that small cells which we used to consider of equal size. Because previously, usually what happens is the size of the compartment is different. So that's why what we consider a small cell inside that compartment. That big compartment, you can think of that as what? Your energy states, and your G or the degeneracy as the number of, or the small that cells which is sitting inside that compartment or the partition. Clear? From that we got a distribution like this, which we use here Stalling approximation, and finally what did we get? We get this expression. This is your distribution function, which was given by gi e to the power minus alpha e to the power negative beta epsilon naught. Now you can see there are two constants sitting over here. One is here alpha and another one is here beta. This was basically what your Lagrange's undetermined multiplier which we used previously. And the partition function is just given by a summation of just this. Clear? Is it clear till here? And this was called your what? Your Boltzmann factor. And basically this is a canonical distribution. So you are getting E, beta E. So now today we are going to do what? How to evaluation of this constants. Now in terms of energy, it was given like this. Now in terms of momentum, can we write this in this form? Because energy can be written as p squared divided by 2m. Because basically what we are just considering the kinetic part of the energy. And we consider that the interaction is very small, which we neglected roughly in your classical statistics. So this is your distribution function. This is given by this. And in terms of momentum, if you write energy in terms of momentum, can you see E has written in terms of P, and energy has been E has been explicitly converted to p squared divided by 2m. Is it clear? Now basically this is the number of molecules in the interval between p minus half and p plus half. This is the distribution function between those small band. Now how do you determine this? Now number of molecule in the momentum interval between basically in dp, p plus dp is basically this one. Or similarly you have that expression, you can directly substitute it over here. This is just this small, can you see this small cell or small this cylindrical spherical cell which is sitting over here, this shaded region. This is just the distribution for given for this. Clear? Now how to determine GP? Now GP dP was what? Your number of cells in that small band. Now that if you all remember, we have determined it previously, which was basically given by volume of phase space divided by its cube. Do you all remember? From which we got exactly this expression for GP dP. For this one, we got something like this. Do you all remember? Do you all remember?
Sir.
Indira?
Yes, sir.
Do you remember?
Yes, sir.
For a kinetic or for a free particle, I think we have done previously at the very starting or at the initial phase.
Yes, sir.
Basically, what you consider a phase space? This is here. What was a phase space? Phase space was basically a 6-dimensional space. Now for timing, I'm just considering 1-dimensional part of this. This is just the representation in two-dimensional plane, okay? This is here x and this is here px. And over here, what will you have? You'll have a sphere. Here in two dimension, you'll have a what? You'll have a circle. Not a good circle, but no, it's slightly better. Now, this is a small region which you have considered between P and dx. This is a small region whose distribution was given by what? N of E was given by, in terms of energy, first let's write in, was given by Z. Z, after that what? Z. Z e to the power negative alpha and beta E by beta E, I believe. G e to the power negative alpha e to the power negative beta E. This was a distribution in terms of energy. Now for your dp in terms of p, what E can be written as p square divided by 2m. For free particle, I think we have done this. And this is just a kinetic part. Now what you have done, you can write this as a function of p, g as a function of p e to the power negative alpha e to the power negative beta p square divided by 2m. Clear? Now, now for the small region between dp, we can write this in this form: beta p square divided by 2m dp. For the small region which is sitting outside, for this small circular cell. But for in terms of three dimension, it will be what? Sphere. It will be certain like this. Sphere, a thin sphere over sphere. This thin part of a sphere. So what you can do after this, you know that GP, dP is basically what? Volume in phase space. In phase space divided by h cube. H cube was the size of a small cell, if you all remember this. And volume of the phase space will be given by what? Integration of, this is a volume integral, so I'm just writing this volume integral of d of px, px, py, pz, and is a 6-dimensional, so you'll have dx, dy, and dz. This is a volume integral, just to make sure, divided by h cube. So this will give you what? Integration over all the space will give you what? Volume, which is basically a volume, will come out. Now you have only an integration of what? Px, py, and pz divided by h cube will be sitting over here. Is this point clear till here? Do you have any problem till here? Any problem? Okay, then fine. We'll move. Now v by h cube dpx dpy. I'm doing the same thing again, dpz. Now if you remember, then what? This will be a sphere in px, py, and pz. Because the x component you have already finished, that will give you this volume in space. Clear? Now, if you remember, it will be a spherical, which have size of what? P. Clear? And the integration of this will give you what? For that small cell which is sitting outside will give you what? First is the surface area, 4 pi. Radius is p, so it will be p square into dp. Is this point clear? Surface area into dp. Is this point clear or not? I can explain it again. Is this point clear or not? Is it clear? because the volume will be 4 by 3 pi r cube or 5p cube. And to get a surface area, you just take a differential of this. If you differentiate it with respect to p, what you'll get? Surface area or the volume element of that small cell, which will be 4 by 3 pi p cube, which will be what? 3 pi p dp. Surface area into this. And 4 is sitting over here, 3 will cancel out. Into dp is the small. So you will exactly get this. So you'll end up with 4 by h cube 4 pi p square dp. So finally, you will end up with which expression? Np dp, you can substitute it by Np dp, you can substitute this by 4 h cube 4 pi v h cube p square, and you have e to the power negative alpha e to the power negative beta p square divided by 2m dp. Now this is an expression for your what? Your number distribution or distribution of particles or molecules. Is it clear till here? Any problem till here? Any problem? Now, if you integrate over all space, this is only for the just for a small cell which is sitting outside over here. Now, if you want to integrate or integrate the whole thing, then what you'll get? You'll get a total number of particles. Total number of particles. If you integrate, basically integrate this, what it will be? It will give you total number of particles. This is basically n. Or should I? Let's write it with capital N. Will be integration of what? Np into dp. That is a total number of particle. So after that you will get what? And the limit should be, the momentum can start from 0, as you can see, and it can extend up to infinity. So the limit, upper limit will be infinity. So the integration of 0 to infinity for h cube p square divided by e to the power negative alpha p square divided by 2m beta times beta into dp. Basically, this thing should come out to be what? Should be the total number of particles. After integrating, what you will get? After integrating, what you will get? Because this is just a constant, you can take this out. What are the constants which are sitting over here? This, and this. Basically 4 pi h cube e to the power negative alpha. So it will be integration from p square e to the power negative p square divided by 2m times of beta into dp. Or what you can do is, we can rewrite this in this form: h cube e to the power negative alpha 0 to infinity p square, beta p square divided by 2m into dp. Now let beta p square divided by 2m is equals to z. You use what substitution? Now can you say this is just like a gamma function? Now you just have to substitute this to something z or something. So your p dp into beta by m, you take a differentiation, will be dz basically. Or here p dp will be what? M by beta dz. Now you substitute this over there. And also you can see a p square will be what? So basically this will turn out to be what? 4 pi h cube e to the power negative alpha 0 to infinity p square e to the power negative z into dz divided by what? Because you have to substitute dp by this one. So m will come over here, p will come over here, and beta will go over here, divided by beta. So which will be 4 pi h cube e to the power negative alpha. One of the p will cancel out, p. So p you can substitute as what? P you can write as 2mz by beta to the power half. It will go from 0 to infinity. P, let's substitute this, 2mz divided by beta to the power half, and e to the power negative z dz. Beta will come over here, so let's write beta over here and m over here for the time being. So you'll end up with 4 pi h cube e to the power negative alpha. This is 2m by beta is constant. 2m by beta to the power half is constant. This is also a constant. Beta by m is also constant. So you're left with 0 to infinity z to the power half e to the power negative z into dz. Basically, what is this? This will give you what? This is gamma of 3 by 2. So this will give you root pi or half factorial. This will give you, which will be equal to how much? Root of pi from the gamma function. You can exactly get this. 4 pi h cube e to the power negative alpha. Beta and m will cancel out to give you what? 2 beta by m to the power half. And this will be root of pi. So now you have a certain kind of relation for your what? For your, for what? For your alpha. So this you can rewrite in this form. In this form, this is basically a total number of particles. Or basically now you can get this e to the power negative alpha. So e to the power negative alpha will be what? H cube 4 pi. Sorry, h cube divided by 4 pi. N will be sitting over here. This m 2 beta pi to the power half will be sitting over here. Now basically this is here what? E to the power negative alpha. So here you have determined what? Your constant, one of the constant. Clear? Is it clear? So this you can substitute this for
Yes, sir.
your this equation for your over here. Now we have found the value of g, you have found the value of beta. Now you are just left with your you have evaluated what? These are some of the expression you have evaluated. G, you have evaluated alpha, and now beta is left. Now you can know what is beta. Beta is 1 by kt. So finally, you can write all the expression combined in terms of, now this was a function of beta. Now e to the power negative alpha you have already determined. So what? 2 kt will be sitting over here. Is it clear?
Yes, sir.
So finally, you're left with what? The expression for your All of you, can you hear me?
Yes,
All of
sir.
you. Actually, so can I use your laptop? Hey, do you have a charger? Can you all hear me?
Yes, sir.
So till now what we have done, we have just found the distribution in terms of momentum. And after that, we have determined few of the constant. We were left with three constants. Those were Z, alpha, and beta. Now first we determined Z, and after that we have determined what is here alpha. Clear? Then now we are left with only one expression, which is what? For your beta. And beta, you know what is beta. Beta was basically 1 by kt. So I'm just going to present it over here. Are you all being able to see this?
Yes, sir.
I'll just recap in the general form. So this was the expression for your first you found the distribution in terms of basically what? In terms of energy. This is a very simple expression. G is sitting over here, one constant, another constant, and another constant is sitting over here. This is called your canonical factor or your Boltzmann factor. After that, what did we do? We wrote this distribution in terms of your momentum simply by changing your energy to p square divided by 2m. This was basically for your free particle. And we have already determined that for the free particle, this still we did. So that came out to be what? Basically this 4 pi p square divided by h cube, this thing. So after this, you have determined what? This constant g. And after that, what you have to find? You have to find expression in terms of alpha. Now we have evaluated the alpha. Alpha had a form of like this. Clear? 2 pi. If you know that I had pi and pi was sitting over here, instead over we can combine this two and write in terms of 3 by 2, which is written over here. Is it clear? Which was equal to your total number of particles. So that we have written in terms of total number of particles. So that's why n is sitting over here. So we can write that expression in terms of this. Now can you see neither g is appearing over here or alpha is appearing over here. Now we have taken care of two constants. Now finally we are left with a single constant, which is beta, and beta is basically what? 1 by kt. Beta is what? 1 by kt. That we have over here.
Beta was what? Basically 1 by kT. So finally you are left with your energy distribution can be written in terms of, now to get back your expression from P to E, what do? You just write energy E as P square divided by 2m. So that's why you are left with E over here. Here will be P square divided by 2m. That has to be substituted. But in terms of P, just write first in terms of P. First just write in terms of P, which is basically this one. Clear? Is it clear? Now if you want to write this is the final expression. Now beta is written by 1 by kT. Now if you want to write this in terms of E, what do? You write this P as what? In terms of energy, P squared 2my in terms of energy. Just substitute this also in terms of energy. This will be 2me, and this dP also in terms of energy, dE. You just take a derivative of that, which will be twice P dE, and P you again substitute in terms of energy. So in terms of energy, you are left with what? Here they have done it, or I have done it. Here you can see this is written in terms of this. So finally you are left with 2m by root pi. Beta is basically 1 by kT E and e to the power negative 2 pi. So finally this is your expression for your energy distribution law. So Maxwell's Boltzmann of distribution of energy. This is how your number of particles are distributed in terms of energy. Basically what did we start? We start with a basic classical particle which are identical, which can occupy any amount of space or any state. Any number of particles can be accommodated in a single state. And from that, what did we find? And they do not have spin. They may have spin, they may not have spin, and they may have degenerate state, or they may not have degeneracy. So this is the expression in terms of energy. This is in terms of momentum, which you are familiar, which we have done. And now to write it in terms of velocity. Now you all know momentum is basically given by mass times velocity. Now just convert this dP. It will be dP will be m dV. So mass will come over here. That mass will sit somewhere over here, and all the expression P you have to just substitute by mass times velocity. So that is your Maxwell's Boltzmann velocity distribution. You will exactly get the expression which you get from the kinetic theory of gases. Clear? So now there we got three kind of distribution. Basically we got three kind of distribution. One is in terms of energy, one is in terms of momentum, and one in terms of velocity. So by using a velocity distribution law, now again what do we determine? We determined here RMS velocity, root mean square velocity, and here most probable velocity. Such thing we are going to evaluate it now by using this Maxwell's Boltzmann distribution law. So we are going to stop it over here.